Hello, I'm Gerhard Larcher, and today I will speak on two quite concrete examples. In fact, I even will speak about three concrete examples because time will allow it. On concrete examples of applications from our work, so the work of my research group, for the financial engineering industry. You can find many such concrete examples in this book here. It's a book on quantitative finance. It was published quite recently. This book contains many concrete examples where financial mathematics is applied for financial engineering. The book is also accompanied by open source software, and you can find this open source software also on this address here in this web page, the LSQF. This stands for Linz School of Quantitative Finance. This book is written in German, but it will appear in English in about 1 year. So this book contains many concrete examples, and in this talk I would like to give you three concrete examples. Three examples where we used quasi-Monte-Carlo, or we try to use quasi-Monte-Carlo, it's work in progress, in a fruitful way. The three concrete topics are pricing of exotic derivatives with Monte Carlo and quasi-Monte Carlo, portfolio selection with many constraints based on artificial intelligence and Monte Carlo, and projected, that's work in progress, on quasi-Monte Carlo. And finally, the third topic on hybrid Monte Carlo in risk management. In all cases, I will give you first the very basic theoretical foundation, so just a sketch of the theory, and then I will show you the software. That's not quite true. I would like to show you the software if I were present in Marseille. So in this form, it's not so easy. So I especially would like to show you numerical tests, which we made to see the convergence behavior of these numerical techniques. Okay, theoretical foundations and then numerical tests. Let us start with the first topic. The first topic, pricing of exotic derivatives. And as I said, I will start with the very basics of the theory. We consider a time period 0 to capital T. Time 0 is now we are in time 0. T is a time point in the future. We consider M different financial assets, and let us say these are stocks, equity stocks, S1 to Sm. This also could be other financial products, but let us consider stocks here. We assume that these stocks follow an m-dimensional Black-Scholes model. That means the following. The price SE of T of the ETH stock at time T is a time point in 0 capital T, has the dynamic DSE is a constant trend factor mu times SET dt plus SE of T times a linear combination of increments of Brownian motions here, weighted by some volatility factors. So W1, W2, Wm are independent standard Brownian motions. So that's the stochastic differential equation system for an m-dimensional Black-Scholes model for M stocks, correlated stocks, of course. If we have this dynamic, then we can represent the price development of each stock explicitly. The explicit form is SE of T is SE of 0 times e to the constant times T plus, and now the sum, a linear combination of the Brownian motions, again weighted with the according volatilities. So this is the explicit form. So we have M stocks, S1 to Sm, and we have a further financial product now, a derivative with underlyings S1 to Sm. We have a derivative D, this will be, we will see an exotic derivative of European style. Okay, what is an exotic derivative of European style? Such a derivative provides at time t a certain payoff. And this certain payoff is a function, a certain given function, a payoff function, which depends, whose value depends on the path of the first stock, the path of the price development of the first stock, the price development of the second stock, and so on, the price development of the mth stock. Okay, so you get a payoff, which is a certain function which depends on the development of the prices of the m assets S1 to Sn. This is an European derivative because payoff is given only in time t, and it's an exotic derivative because the payoff depends on the whole passes of the assets. And then the basic problem in derivative pricing is, what is the fair value? We call it f of 0, the fair value, the arbitrage-free value of this derivative at time 0. Just some examples of such exotic options. One example is an arithmetic Asian call option, for example. Here the payoff does not depend on the whole pass, but we choose capital N time points, T1, T2 to Tn between 0 and T. Then we consider the arithmetic mean of the stock at these time points. So I've forgotten to say, let us consider, for example, m equal 1 also. The underlying is just one stock, not m stocks, just one stocks. So we have n time points. We consider the arithmetic mean of the prices of the stock at these points. We compare with a certain pre-chosen so-called strike k, take the difference, and the payoff is the maximum between 0 and this difference here. That's the payoff, and this is an arithmetic Asian call option. Such arithmetic Asian call options are frequently traded. One very well-known and frequently traded such product are the so-called TAPOS, with underlying the aluminium price, and they are traded at the London Metal Exchange, for example. The geometric Asian call option is essentially the same, but instead of the arithmetic mean, we now take the geometric mean of the price values of the stock S. Another example of an exotic option, exotic derivative, is a so-called multi-asset look-back call option. Here again we have M underlying stocks, S1, S2, and Sm. And here the payoff is the following. For every E, for every stock E, we consider the relative growth, so SE of D divided by SE of 0. And then we consider the maximum of this relative growth over the whole time interval, so maximum over all T. And then the maximum of this maximum taken over all E from 1 to n, over all stocks. So the absolute maximum of the relative growth of all stocks in this time interval. We can compare with a certain strike. The payoff is the maximum between 0 and this difference here. So these are some examples of exotic options. So how to find the fair price, the arbitrage-free price at time 0 of such a product? The answer gives the classical Black-Scholes theory. Very beautiful answer. The fair price of the derivative is nothing else than the discounted value. Discounted R is the risk-free interest rate for the period 0 to capital T. The discounted value of the expected value of essentially, and here's essentially the payoff. So the expected value of the payoff. Okay. But here we have S tilde instead of S. So what's this S tilde? S tilde is nothing else but the S here, the dynamic of S here, but with this mu E, for every E, replaced by the risk-free rate R. Okay? So the fair value is the discounted value of the expected value of the payoff, but not taken over the assets S1 to SM, but to S1 to SM tilde, where S tilde has the same dynamics as SE, but mu E replaced by R. So we have to calculate this expected value E. In some few cases, E can be determined explicitly. Such examples are barrier options, the geometric easing call option, but not the arithmetic easing call option, and some others. In most cases, of course, we have to use numerical methods. We have to approximately evaluate this value E. And how can we proceed to numerically evaluate this E? One approach is the following. Again, we discretize the interval, the time interval 0 to capital T by time points T1, T2 to Tn between 0 and capital T. Then we approximate the payoff phi, the payoff with respect to S tilde, of course, by some suitable psi, where psi now is not a function of the whole path, but of S tilde TL L equal 1 to capital N. Here again, this should be TL, the last, instead of T2, this should be TL. Okay. This. So, okay, then to approximately calculate phi, the expected value of phi, we have to approximately evaluate the expected value of psi. Now we note that because of the explicit form of the stocks, you can see it in this line here, we know that for every time interval, time point TL plus 1, S tilde E of TL plus 1 is S tilde E of TL times E to this constant times the increment of the times, plus the sum of sigma Ej square root of the increments of the times, times WJL, where the WJL, J runs from 1 to M, L runs from 1 to N, are N times M independent standard normal distributed random variables. Okay, and if we insert this here in this value here, then we can see that this function psi is nothing else than a function g of these variables W11 to Wmn, which are independent standard normal distributed random variables. So to approximately evaluate the expected value of phi, we have to evaluate the expected value of g. What's the expected value of g? It's the integral here, the integral minus infinity to infinity. It's a m times n-dimensional integral over the function g, weighted with the density functions of the standard normally distributed independent random variables. And that means that f of 0, so the fair value of the derivative, is this shouldn't be an equality sign, it should be an approximately sign. So f0 is approximately the discounted value of this high-dimensional integral. And to evaluate approximately this high-dimensional integral, we have to use, in most cases, we have to use numerical integration. As I told you, we have provided software for my book, extensive software, and for example, also extensive software for pricing all kinds of derivatives, standard derivatives, exotic derivatives, explicitly, if possible, or with pure Monte Carlo, or with Monte Carlo with variance reduction, or with quasi-Monte-Carlo. Here I don't want to show you the software, it's not really possible here. So I just want to show you some simple single example, namely let us consider the multi-asset look-back option, which I have already shown you in the examples. You remember, for such a multi-asset look-back option, the payoff is given by the maximum over zero, the maximum over all relative growth, over all time points and all assets, compared with K. Then we approximate this payoff by dividing the time interval COT by time points T1, T2, Tn, and so on. And we approximate the overall maximum by the maximum taken now over these time points TL. Okay? So instead of taking the maximum over all T, we take the maximum over these time points. So here we have the approximation, which I showed you before, where we approximate the payoff phi by some approximate payoff C. Okay, so that's the approximation. Then we can carry out, then we can insert this into the integral, and then we can carry out Monte Carlo integration or quasi-Monte Carlo integration. And just to give you a feeling about the behavior of these methods, let me show you just one concrete example. Here we value the multi-asset look-back option, which is based on 10 correlated stocks. We carried out numerical integration with 50,000 sample points. The blue line is, or let us start with the black line. The black line is the exact value. It's hidden here under the green, the red value, and it was calculated by really extensive simulation. So that's the exact value. If we approximate with the help of Monte Carlo simulation, we get this kind of convergence here. That's a typical picture, okay? If we consider, or if we use quasi-Monte Carlo with the help of the Holton sequence, then we get the behavior of the red line here, and you see extremely good convergence. If you use quasi-Monte Carlo with Niederreiter, then we have the green line here. I would like to zoom out the first 5,000 sample points, and you see it a little bit better. So the quasi-Monte Carlo approach is much better than the Monte Carlo approach, and about the same behavior for Holton and Niederreiter. So this was just one example of a numerical result. You can find this software at accompanying my book or on our homepage. This was the first application. The second application now is portfolio selection with many constraints based on artificial intelligence and Monte Carlo. Again, I will start with the basics, the very basics. So I will sketch classical portfolio selection theory in a nutshell. Again, we have a time horizon, 0 to capital T, 0 is now. We have some free cash for investment. For simplicity, just say our investment is €1. If you prefer, you can also think about 1 million euro, for example. It doesn't matter. Again, we have M different financial assets, and again, let us speak about stocks, equity stocks, A1 to AM. To use now the classical portfolio selection theory, we need estimates, good estimates for several parameters. Namely, we need good estimates for the expected returns, the expected trends, mu1 to mu_m, of the stocks A1 to AM in the coming time interval. We need good estimates for the expected volatilities, sigma 1 to sigma m of the stocks A1 to AM in this time interval. And we need good estimates for the expected correlations, rho EJ, between the returns of each pair AE, AJ. Assume for the moment that we have good estimates for these parameters. Then we can represent every asset, every stock AE, by the value sigma E, mu E, by the estimated volatility, the estimated trend. And we can illustrate the AE in a volatility trend coordinate system. Okay, so we can draw all this AE in this diagram. Then we should invest our 1 million euro. To do this, we choose x1 to xm, larger or equal to 0, so that the sum of these x1 to xm is 1 million euro, our investment. And we invest xe euro in the asset AE. We write this formula in the following way. We get therefore an investment portfolio P, which I write as x1A1 plus x2A2 and so on, xmAM. This means invest x1 euro in the asset A1 and so on. For this portfolio, we can again calculate the trend, the expected trend. It's just a linear combination, x1 mu1 plus x2 mu2 and so on. And we can calculate the volatility of this portfolio by using the volatilities of the stocks and by using the correlations between each of the two stocks. And again, we can draw this portfolio into this diagram here. If you do this for all possible choices, x1 to xm, positive with sum equal to 1, and if we draw them all into this diagram, we get something which usually looks essentially like this figure here. So all possible portfolios are in the inner of this figure, of such a figure. Okay, here are all possible portfolios which you can build from A1 to AM. The left upper part of this figure is the so-called efficient border. Why is it called efficient border? Because it only makes the sense to invest in portfolios which lie on this efficient border. So why is this the case? Consider an arbitrary portfolio. So for example, this here. Then in any case, you can find a portfolio on the boundary, on the efficient border here, which is better than the red portfolio, because it has the same risk sigma and promises a higher return. Okay, so this in any case is better, and this holds for every portfolio in the opportunity set. You can find a portfolio on the efficient border which is better. So it does only make sense to invest in portfolios in the efficient border. But in which portfolio should you invest on the efficient border? Here also the Markowitz portfolio selection theory gives an answer. The answer is very well argumented. I just give the answer without the arguments. You have to determine the portfolio with the maximal Sharpe ratio. The Sharpe ratio is the following. You consider the expected trend of the portfolio and compare with the risk-free interest rate. Of course, this should be positive. Otherwise, you would not invest in this portfolio, but just in the risk-free interest rate. So you consider this difference here, which should be large, and divide by the risk, which should be small. You determine the portfolio with the maximal Sharpe ratio. This geometrically, this can be done in the following way. Here again, we have the opportunity set and the efficient border. You start with this point here. This point, I did not label it, did not name it. This should be the point 0, sigma equals 0, and mu equal r. So this is the point 0r here. are the risk-free rate. You start with this point and you take the tangent from this point to the efficient border, and then this is the portfolio's maximum Sharpe ratio, and Markowitz's portfolio theory says invest in this portfolio. So the theory, it's a very beautiful theory, but of course there's one big problem, namely to give good reliable estimates for the parameters, especially for the parameter trend, expected return of stocks in future time period. So how to give really good estimates for expected return of stocks in the future. That's the big problem. Of course, there are several attempts to give good methods to overcome this problem, so-called single-factor models, multi-factor models, Black-Literman model, and so on. But the problem remains. We had a cooperation with a FinTech company who asked us to improve this system, this portfolio selection system, and to implement a very good, very fast such system. And we tried to overcome the problem of trend estimating, expected returns, by introducing a new quality measure. A new quality measure which especially works if the underlyings are not single stocks but funds, investment funds. This new quality measure, we will call it FinTech ratio, XI, is based on artificial intelligence techniques. However, it cannot be the topic of this talk how we developed and how we constructed this FinTech ratio. Okay, but essentially we did a classical portfolio selection theory, but using this new parameter xi, which can be estimated much better with the help of AI techniques instead of the trend parameter mu. Okay, that's the only difference. Okay, but of course, in reality, there are many further challenges than just basic setting. I just would like to give you some challenges we had when we worked on this concrete project for FinTech. In real applications, we have to deal with many more constraints. For example, we have to deal with, in our concrete application, we have to deal with really many basic products. In our application, our bases were given by a universe of 33,000 investment funds. Not only 10 basic products. Then we had constraints of the following form. If you create a portfolio, such a portfolio should not contain too many elements. It should contain only a maximal number M of products. For example, maximal 10 products where you can choose this M as you want. Then each product in the portfolio should appear with a minimum percentage. Okay, every product in the portfolio should appear with at least 3%. Further challenge, a further constraint. Funds, more and more funds have a certain sustainability number, okay? Number between 0 and 1. And many investors like to have funds with a high sustainability number. And so we also have implemented in our program, in our software, the possibility that we just choose portfolios who have a sustainability index above a certain level, which you can choose. For example, at least 0.6. Further constraints. The portfolio which we generate should reflect approximately a certain pre-chosen diversification about regions. For example, 40% United States, 30% EU, and so on. The portfolio should reflect approximately a certain pre-chosen diversification about branches. For example, 30% IT, 20% chemistry, and so on. The portfolio should reflect approximately a certain pre-chosen diversification about fund management styles. Okay, for example, 60% should be active managed funds, 40% passive managed funds. Further constraints with which we had to work. The portfolio should reflect approximately a certain pre-chosen diversification about different product types. For example, it should contain at least, at about 40% stocks, at about 30% bonds, about 20% commodities, about 10% alternative investments. The portfolio should be contained in a certain predefined risk class. And last but not least, the following constraint: the algorithm should choose with higher probability funds which are preferred by the investment advisor. So the investment advisor uses our program to advise his clients how to create, how to generate their portfolios. And of course, in many cases, the investment advisor has some favorites. And he would like that these favorites are chosen with a higher probability, but nevertheless, he wants that the best possible choice is done. Okay, these are some constraints, and by far not all constraints. What's the straightforward strategy? Indeed, we used this straightforward strategy. Of course, if we have to deal with 33,000 funds, we have to do a pre-selection in a certain sense. Okay, that's not really the topic of our simulation here. We have to carry out a certain pre-selection. Then we choose by random at most M funds. You remember we had the constraint that in a portfolio there should be contained at most M funds. So we choose by random at most M of this universe of possible funds. Then we choose by random positive numbers x1 to xm, whose sum is equal to 1. Then we build the portfolio x1 f1 plus x2 f2 plus xm fm. We carry this out very often. In fact, in our program, we have carried this out several hundreds of millions times. From these several hundred of millions possible portfolios which we have created, we choose the portfolios which satisfy the constraints in the best way. Say about 100,000 of the portfolios which satisfy the constraints in the best way. And out of these 100,000, for example, portfolios, we choose the portfolio with the best FinTech ratio. So that's the straightforward strategy to carry this out, to find a good, very good portfolio with a high FinTech ratio and which satisfies the constraints in the best way. We have certain strict constraints. They have to be satisfied. And we have certain soft constraints which should be satisfied approximately. Okay, that's the challenge. Just a side remark, I said here, choose x1 to xm positive whose sum is equal to 1. Just a side remark or warning. If we have to generate x1 to xm whose sum is equal to 1, then near at hand approach to this is that we choose y1, y2, ym, positive random variables. Then we normalize them. So we divide each of these random variables by its sum, by the sum of all these variables. Then you get positive random variables whose sum is equal to 1. Just a warning. If you choose this approach, do not choose y1 to ym uniformly distributed and then normalize them, but choose y1 to ym exponentially distributed and normalize them. So why is this the case? I'll show you an illustration. If you choose the first approach, if you choose y1 to ym uniformly distributed and then normalize them, then you see x1 to xm equal to 1 is a m-1 dimensional set in the m-dimensional unit cube. So for example, I've drawn here a picture for m equals 3. Okay, here are the points x1, x2, x3, whose sum is equal to 1, which were found by the first method. Then you already see that here we have a concentration in the center. Okay, it's not a uniform distribution, this triangle here. But if you choose the exponentially distributed approach, if you choose y1 to ym exponentially distributed, then you get this picture here, and you see a very well distribution in this triangle. So this doesn't look so dramatic, but it becomes more and more dramatic in higher dimensions. It becomes much worse in higher dimensions, and you just get weights in the center here, and then almost no weights in the boundary. Okay, our program, which we developed, contains many further features. Just want to point out one. It also can do the following: if there is already an existing investment portfolio, and you or your advisor wants to extend or to rearrange this portfolio in an optimal way, you would like to do this with just a few purchases and just a few sales. You don't want to destroy the whole portfolio and build a very new portfolio. You want to do this with just a few purchases or sales, and our program can show how this can be done in the best way. So here in this place, I would like to show you the program, but hopefully maybe once we can meet personally, and then we really can test together this program, and it does not really make sense here online. And so we have time, at least we have time to go to our third topic, but before we come to the third topic, I just wanted to say the following. We have carried out this software program. We have developed this software. It's used now by a big German insurance company, for example. We have used until now Monte Carlo, but you remember it's a quite challenging simulation program, which we have to handle here. And it's work in progress now to use quasi-Monte-Carlo in a fruitful way, and to use quasi-Monte Carlo such that it really gives really better results than Monte Carlo, and even really better results, which is measurable that they are better results. Okay, that's work in progress now. Okay, now our last topic. I think I have still about 10 minutes, and this will be sufficient. The last topic, that's more of a theoretical form. We've not yet implemented it for real users. We deal with the system credit metrics of JP Morgan. So with credit risk management. Again, the basics. We have to deal with a credit portfolio, K1 to KS. These are S credits. Let's assume that they are just bonds. Okay. Every credit is given to a certain credit receiver. The credit receiver for these are bonds usually is a company. So let's speak. The KE is the credit, or also the credit receiver, the company which receives the credit. So assume that for every credit KE, we have the rating of the company. For example, Standard & Poor's rating, AAA, AA, D. The credit has a certain maturity. It has a face value, for example, 100 million euro. The annual coupon, which has to be paid by the credit receiver, and the credit belongs to a certain security class. If we have these values, these dates, then we can calculate at the fair value of this credit KE on the assumption of certain credit spreads. Okay, we can calculate the current fair value of each of the credits. We can sum it up, and this gives the present value of the credit portfolio. The fair present value of the credit portfolio, we will call it A0. In credit risk management, however, we would like to know something about the value of the credit portfolio in 1 year. Okay, we will call this A1, and A1 of course is a random value. We don't know exactly now what's the value in 1 year. And here comes the asset value model of JP Morgan to play. Under certain assumptions, based on this model, we can get information about this A1. Okay, and the 3 assumptions of JP Morgan, the asset value model, are the following. If you consider the asset values of companies, and if you consider the asset value changes of companies within 1 year, then the first assumption of the asset value model is that these asset value changes within 1 year are normal distributed. The second assumption is the joint distribution of asset value changes of any 2 companies within 1 year are binormal distributed. And finally, the third assumption of the asset value model is the following. There's a one-to-one dependence between the changes of the asset values of the companies within 1 year and the changes of the ratings of the companies within 1 year. So if in the coming year, the asset value of a certain company changes very positive, it increases very much, then it's very likely that also the rating of the company becomes better and vice versa. These are the 3 assumptions, and then we can carry out, based on these 3 assumptions, we can carry out simulation. In the following way, we generate S standard normally distributed random variables, x1, x2 to xs. S, remember, S is the number of credits. Then we transform them such that they have correct correlations. Then we get the vector y1, y2 to ys. What do I mean by correct correlations? The y1, y2 to ys will represent the normed asset value changes of the companies K1 to Ks within 1 year. Of course, there's a correlation between the asset values of the companies K1 to Ks. Okay, and the y1 to ys should have the suitable, the according correlation. Okay, we transform the x1 to xs standard normal distributed random variables, and I've forgotten to write here independent. Generate S independent standard normal distributed random variables. Then you use Cholesky decomposition to get the right correlation. This represent asset value changes of companies within 1 year in this one simulation scenario. Then by assumption 3 of the asset value model, this leads to new ratings of these companies within 1 year. And if we know the new ratings of these companies in 1 year, then this scenario leads to concrete value A1 of the credit portfolio in 1 year. So one such simulation scenario leads to one realization of the random variable A1. Okay, y1 to ys leads to one possible value for A1. What would we like to know? We would like to know the expected value of A1, the value of the credit portfolio in 1 year. We would like to know the variance or standard deviation of the value of A1. Both things based on the asset value model of JP Morgan are exactly possible. Okay? But for risk management, for calculating evaluate risk, we need percentiles of A1. For example, the 1% percentile, we will call it alpha, of A1, of the value of the credit portfolio in 1 year. And for this, we need simulation. We cannot give exact value. A1 is not normally distributed, so we have to use simulation. How do we do this? Of course, we do it in the following way. We generate y1, y2 to ys very often, say capital N times, and we get an empirical distribution or a simulated distribution, and from this we can estimate alpha. Okay, so we have to simulate. Note S is usually very large. Number of credits in concrete applications is usually very large. So the credit portfolio of a bank usually is much larger than 1,000. Okay, so we have a very high dimensional simulation problem. Should we work with Monte Carlo? Should we work with quasi-Monte-Carlo? It turned out that in most cases, if S is large, and S is large in most cases, and if N, the number of scenarios which we can generate, is realistic, then in most cases Monte Carlo gives sometimes even much better results than quasi-Monte-Carlo. But we also found out that a certain hybrid version sometimes can give essentially better results. I will explain you in a moment what I mean by a hybrid version. We have developed a hybrid version for which we know that it's never worse than Monte Carlo. Remember, Monte Carlo is the better one. In most cases, Monte Carlo is better than QMC. The hybrid version which we used is never worse than Monte Carlo, and sometimes it's significantly better than Monte Carlo if it's carried out in a suitable way. So what do I mean by a hybrid version, by hybrid Monte Carlo? I mean the following. You remember we have to, for each single scenario, we have to generate such a vector y1 to ys, okay, of normally distributed random variables which are correlated in the right way. Now we choose t rather small compared with s. T rather small, and we assume that the credits k1 to ks are named or labeled in the following way, that k1 to kt are the most risky credits. What do I mean by most risky? These are credits which have a very bad rating, which have a large face value, and which belong to a low security class, okay, high risk. T should be rather small, that is a suitable application of hybrid. T has to be rather small in comparison with S. And we choose y1 to yt, so the first part of our vector, by quasi-Monte-Carlo. And the second part of the vector of length s minus t is large, and these represent the not so risky credits. For this, we just use Monte Carlo. Of course, we have to take care that this quasi-Monte Carlo method here is uncorrelated, independent of this Monte Carlo method. Okay, and then we work with these vectors. It turns out that for homogeneous credit portfolios, so where all credits are at about of the same risk level, hybrid Monte Carlo behaves essentially equal like Monte Carlo, so never worse. For inhomogeneous credit portfolios, however, if there are some credits which are much riskier than the most other credits, it turns out that hybrid Monte Carlo is sometimes much better than Monte Carlo. And this is the finish of my talk, would like to show you some pictures to convince you about the convergence behavior of the methods, and this again are very, very yes, it's typical that this performance happens. You see here we have the case here of 500 homogeneous, but 500 homogeneous credits, portfolio of 500 credits which are all of about the same risk class, and we just used up to 5,000 simulations. And you see quasi-Monte Carlo, the convergence of quasi-Monte Carlo is rather bad here. The convergence of Monte Carlo is quite good, rather good. And hybrid simulation, it's the pink curve, is, you can say, a little bit better than Monte Carlo. It converges a little bit earlier. The red line is the exact line. You remember, we can give the exact value for the expected value. Here, the standard deviation of the same example, you can see quasi-Monte Carlo is worse. Monte Carlo, the blue convergence, and the hybrid, the pink convergence, are quite well. And here it's the behavior for the alpha, the first percentile level of the portfolio value. For homogeneous portfolio, you see Monte Carlo and hybrid much better than quasi-Monte Carlo. And again, already here, hybrid is even better than Monte Carlo. Here, our second and last example, we have a portfolio of 1,000 quite inhomogeneous credits now. We have used now 10,000 simulations. We have the convergence of, it's again the expected value first, convergence of quasi-Monte Carlo, the convergence of Monte Carlo, and significantly better the convergence of hybrid Monte Carlo here. Same picture for the standard deviation. Again, Monte Carlo, hybrid, here about the same, but in any case better than quasi-Monte Carlo. And here the picture for the first percentile level of the portfolio. So that's an idea of how to combine Monte Carlo and quasi-Monte Carlo in a good way. So these were the three concrete examples. Thank you for your attention, and I hope to see you soon in Marseille or in Linz. Thank you very much.